Mansour die werkt daar veel in mee. Ik heb natuurlijk al een postje op Blackboard gedaan waar een uitleg staat waar Mansour het over gaat hebben. Hij zal zichzelf straks ook nog even verder voorstellen. Maar ik ga er zelf ook even bij zitten, want het lijkt me hartstikke interessant. En I'll give the word to you, Mansour, and well, take it over.
Thank you much for the introduction, and thanks everyone for coming here today. So today's guest, I'll be today's guest lecturer. My name is Mansour, and I'm completing my studies in the University of Groningen in the artificial intelligence faculty. And I'm also working as a data scientist at Researchable already for 1 year. And yeah, so a little bit about Researchable. It was founded in 2018 by Frank and Ando, and both of them are postdoctoral researchers, and they love computer science and love developing software. And they figured that, well, Researchable could basically make applications and like software development, data science, and stuff like that for both university, also organizations, and help them make applications which can manage data, they can use data, and then can analyze data using machine learning and other cool stuff. And also we're part of numerous coalitions such as AINL, Smart Industry Hub, NL AI Coalition. And yeah, so the company grew in 2019 during COVID, and then we had a lot more projects. And then, we joined the industry, so we figured that researchers are not only the ones who could also help, but we could also help the companies in the industry, and that's how we expanded. And in 2021, we've got ISO certified, which makes us more reliable, which makes us more friendly for the companies. They can see that they can trust us, and we can manage their data. So we have many partners, maybe some of them you know. We have TU Delft, UCL, University of Groningen, UMCH, and many others. Some of the projects I could probably want to mention is Sports Data Valley. It's a national platform, Dutch national platform for analyzing sports data. EV, it's a database management for very high dimensional molecule data. And also ACIDA, it's basically a platform for automating data science for data scientists. And it was used for example, managing water pipelines. Very cool project, I think. Today we'll be focusing on data engineering. We'll be talking a lot about data. I'll be saying data a lot of times. And we'll talk about data, big data in general, and how to store and process it. So I think the first question to ask is, what is data engineering, right? So this is an example from Wikipedia. It says something about building systems enabling collection and usage of data. Interestingly enough, there is nothing said about AI, and we'll come back to that later. Maybe this is not the right question to ask, right? Maybe the more appropriate question to ask is actually, what is it that the companies actually want from data collection systems, and what do they find useful in the data collection processes? Nowadays, companies collect a bunch of data. They collect so much data that no one can even imagine that much, right? And it's actually the process of figuring out what is it that you actually want to know from this data. It's finding basically a needle from a haystack, finding something important in the data. And what exactly could you do with it? So I think this is a very interesting diagram, and it shows how mature is a data analytics field inside a company, right? So very low mature data analytics group could be like answering questions such as like, what happened based on data and why did it happen, right? And then they could use some human input to later make some further decisions and taking actions, right? But in the higher companies, they are so big, they have to automate most of these processes and actually make it much faster, more durable, and more easily manageable, right? So they progressed to actually prescriptive data analysis, which actually tells you what should you do. So it helps you plan, for example. It makes you take decisions and even make automated decisions. And yeah, this is a very interesting diagram. It was taken from Gartner. Maybe later you could, if I share the slides, you can take a look at the article. It's quite nice. So a little bit about data. What is data? Well, data is very multifaceted, right? It has a bunch of types. It could be financial data. It could be data about traffic and sensors and all of that. But I think the most important and most relevant and most interesting data is the real-time data. It is data, for example, collected from the sensors. It is data that is collected from how users are doing right now on the platform, how many people are watching, and that is important to the companies to know how well they are doing. So also, importance of data is very visible from the size of data we have right now. So in the 80s, there was like little to none data. Not a lot of companies actually collected data about themselves, how well they are doing, and made decisions on that. But now if you look at how we're doing, it's actually crazy, because in the last 2 years, we have generated 90% of the data that there is ever created. Can you imagine that? It's crazy. And the scale of data increases every time, every day. And it not only increases, it helps you to make decisions. It helps you to make applications. You can take data and create insights from it. That's what data scientists do. They process it, they create new insights, and then take decisions upon that. And that, again, processes new data. So you get more and more data. It just creates itself, and too much. Now, a little bit about big data. Does anyone know what is big data? Maybe a show of hands would be nice.
Yeah, more data than you can manage. I think that's the definition.
Okay. Anyone else? That's a good attempt. So, how I would define big data? It refers to data sets which are too big and too complex for you to actually manage and do processes on to infer information from, right? And I think a great way to actually look at it is through the big data's 5 V's, right? So it is volume, velocity, variety, value, and veracity. If you go about it bit by bit, so volume refers to like how much of the data you actually have, right? So the more data you have, usually it's better, because there's more chances of actually there being some informative information inside it, right? The more you can extract from it, and the more you can find out and maybe take some, maybe have some advantage among others. Velocity refers to how quickly you actually get that data, how often you create this data. For example, later we will see examples where there is so much data created you cannot even just imagine that, and that is also very useful. Variety refers to how diverse is your data, right? So there is data such as structured data, which refers to tables, refers to reports, spreadsheets, stuff like that, and there's also unstructured data, which is videos, images, audio, and that is also very important for the companies because, well, that is also data, and it's much more easily produced. It's produced much quicker. Literally, YouTube produces a huge amount of videos every day. I actually don't know the number, but I know it's huge. Value. Well, of course, the value of the data has to be, well, it is valuable, right? Because, well, how much data we have, how much data we collect, it possesses a lot of information for you that you can use to take actions. And veracity, it's how truthful is actually your data. So you have to trust your data, that it's actually from the reliable source that you can actually, decide upon. So this is how basically big data is evaluated and how it is looked upon. Now a question for you guys is, how much do you think Facebook produces data per day? Any guesses?
Terabytes.
A terabyte? Okay. Any more?
Millions of terabytes.
Millions of terabytes. Okay.
Exabytes.
Exabytes. Well, it's actually 4 petabytes per day. Okay. So let's just let that sink in. Okay. 4 petabytes. Your computer, my computer, can hold a terabyte of data. Okay. And mostly half of it is taken by Windows or something like, and the rest is used by me. And now imagine a petabyte is 1,000 of them. So it's 1,000 terabytes. And this is 4 petabytes per day. That is crazy. How do they even manage that? How do you even work with such amounts of data? That is the big question. Maybe another example could be useful. Does anyone know what this is?
Sen.
What?
Is the
Large
last
hybrid cooler.
accelerator.
Yes. It's a large hadron collider, and it is very huge. And I don't know if you've noticed, there is actually a person down there. So like, just imagine the scale of this thing. It's 25 kilometers in diameter, as far as I remember. And yeah, it's basically a particle accelerator that pushes neutrons and ions near the speed of light. And then the researchers collect that data and then analyze it, and they make inferences about that data. All right. So let's look into that. Well, first of all, when they actually launch it, they have the input stream of data. And when it is produced, they produce 70 terabytes of data per second. 70 terabytes. Although most of it is noise, right? Most of it is not useful data. So they actually have to process it. It's done quite quickly. And then in the end, they save around, let me see. Yeah, about 15 petabytes per year. The reports are quite diverse. So some of them say they analyze around 25 petabytes and distribute it around the world. Some of them say it's 200 petabytes. But still, those numbers are huge. Right. Basically, big data is too large for traditional software to process. Your algorithms probably will not be able to run that. I have a hard time running a terabyte of data through my machine learning pipeline, and just thinking about petabytes of data, even 1 petabyte, that's crazy. How do you even manage that, right? How do you get that petabyte on your computer? How do you run that? How do you process that? How do you infer something from that? And so here comes a lot of challenges. How do you process 1 petabyte? First of all, the performance is scalability. So performance is very dependent on scalability. How well can you actually scale, right? So it could be you have multiple computers, you have multiple servers which actually take action on top of the data, they process it. You could also use GPUs, for example. This is scalability, right? So this is very important, and yeah, just this is how you actually have to approach data. If you are not scalable, then your performance might be lacking. Of course, there are also other challenges in the data. So for example, concurrency. So are there any tasks that are blocking one or another, right? Because if they are blocking one or another, then you'll not be able to ever have an efficient algorithm which can actually process this much of information. There's also a problem of distributing. So how do you distribute the workload? How do you distribute it through the different computers? If you're running multiple servers worldwide and you're running all of the data processing, how do you actually manage this? How do you even control all of this? And apart from that, also in distributing goes the managing the data. So the data is stored somewhere here, then it has to go here, and then it is going here. So all of this path takes some time. And you have to be very efficient. So your computers, which actually process the data, have to be quite closely placed next to the the storage basically has to be next to the place where it's actually processed. So this is the distributing problem. Data sharing. well, if you actually want to have the reports, if you actually want to know how your pipeline is doing, it has to be easy, right? So if there is a problem in the pipeline, you have to know that quite early. You have to be able to easily collect what information is there in the pipeline. How is it doing, right? And yeah, the access also has to be shared, and all the processes have to have the correct accesses that there are. Now, 28 slides in, we're ready to actually talk about AI with big data and machine learning. And now we can discuss more about this. So I think this diagram, it provides a very good explanation of what is the role of actually machine learning and AI in the whole data engineering, data science process. So you can see it's only this part, and the rest is monitoring and classifying and figuring out how do you actually process this data. This diagram is taken from the hidden technical debt in machine learning systems, and also a very nice read, I think. And there is a quote in it that says that the hardest problem in scalable AI is not the AI itself. Okay? It's actually managing the data. And this is something that companies overlook. They don't consider that. They think that, oh yeah, we'll just have a bunch of machine learning engineers, we'll have AI people, they'll AI something, and then we'll be good, right? We'll have profit or stuff like that. But of course, that's not the best way to think about it. So you always have to consider the overhead. So it's the data processing, how do you collect it, where do you store it? And this is not something that everyone looks into. And yeah, you're not alone in that. Many people have faced these issues, and they have solved it. And this is a huge diagram of all the AI applications, or at least a subset of these AI applications, and that help you to actually manage your data, store it, log it, you name it, right? It's huge. So definitely, if you have a problem, you will find the solution somewhere in there. And today we'll be only focusing on one of them. Oh, wait, sorry. Yeah. Has anyone had experience with any of these apps? Or maybe...
The one in the middle.
The one in the middle. Yeah. So some of them are, I don't know, quite popular, like Jupyter Notebooks, Anaconda, D3 for visualization, maybe Power BI, PowerPoint. Yeah, you probably know Siri, you know Alexa, which actually do speech recognition, and many more applications. So many of them you actually maybe know, maybe you've worked with them, but you haven't actually realized that. And yeah, today we'll be only looking at a tiny fraction of it. Just imagine how many applications there are, and we'll be only looking at this one, right? Let's zoom in a little. It's called Delta Lake. Okay. So Delta Lake, here's the description from the Delta Lake website. Sorry to put the huge wall of text on the slide, but basically if we shorten it, yeah, Delta Lake is an open source storage layer that brings reliability to Delta Lakes. Right? Delta Lake provides ACID transactions, scalable metadata handling, and unified streaming of batch and processing. Right? And it runs on top of Delta Lakes, and it's compatible with Apache Spark APIs. Interesting, right? From all of this, you can know that it is open source, so you can trust it, right? It's very nice because, well, a lot of companies prefer to have open source technologies in them. It's reliable, and especially on Delta Lakes, which we'll cover a little later what Delta Lakes are. It has ACID transactions, which we'll look into right now. Scalable metadata handling, which is useful. For example, like what is your metadata? What is your data? So it describes where did you get it from? How did you get it from? What processes did it go through? Right? And you'll have to know all of that if you have, for example, an error somewhere, then you have to backtrack it. That's what you can use the metadata for. It unifies streaming and batching processing, which we'll also look into. And yeah, it has Spark. Has anyone worked with Spark before? No? So basically it works on top of this. So when you actually have a Delta Lake, you can, well, you have to work on it somehow, right? So you can use like Python, you can use sklearn or something like that to do your machine learning and data analysis. However, Spark implements an exactly similar API to similar of like SQL or what you do in Python. But it also distributes it among multiple computers, multiple machines, and that allows you to make it very fast and efficient. So yeah, first let's look into ACID transactions. What are these? So ACID is basically an acronym for atomicity, consistency, isolation, and durability. So first is atomicity. So this refers to the integrity of the entire database transaction. So each action that is done is basically atomic. So it is separate from every other action. And if it fails, then the whole pipeline fails. So it will not ruin your data. It will not add any corrupt stuff to your data. So now you know that, okay, your data, however it has been processed, it's okay, right? It's isolated. Yeah, next part is consistency. So yeah, we talked something about schemas before, and the schemas are basically introducing consistency in your data. So sometimes you may be doing something in your data, and then you're like, oh, I overrode this column. And that is not good, of course, because now you could lose some part of the data. And having it being consistent, having a schema, basically stops you from doing any errors like that. Next is isolation. So it refers to doing multiple transactions at the same time, independent of each other. Okay, so it's this job is not in any way influenced by the other job. For example, you have like multiple steps in the processing of data. Each job knows that it has a job as the data, and it just accesses the data, and then it processes it separate from all the other steps. And durability. This means that, for example, if something gets corrupted, right? So if the system, for example, gets shut down, or the data center gets, I don't know, stopped the energy or something like that, then the data does not become corrupt. So it goes very hand in hand with atomicity of the pipeline. So yeah, now let's kind of go through a example use case of how you can use Delta Lake. So an example could be like sport data management. So you have a bunch of sensors on people, or for example, on the football field, you record people, how they're moving around and so on. And then that data is stored somewhere. It is processed. And then you create like some hard predictions. For example, you run through your machine learning model and something like that. And then reports are created, for example, through Power BI or something like that. That would be like a typical pipeline, more or less. And all of that can be done through Delta Lake, because Delta Lake both allows you to it allows you to store data, but it also allows you to actually store the process data of that. So it allows you to have everything in one place at the same time, and it allows you to have very simple access, so that everyone can know access what is relevant for them. Nice imagery for you to relax. Yeah. Let's first look into how actually Delta Lakes came to be, and how is it constructed, and what is the motivation behind them actually coming by. So we can kind of divide it into two processes. First one we said is the storage part, and then the other one is the processing part. So first is the storage. So initially, like in the 80s, for example, there were something called warehouses. Warehouses basically allow you to store data. Mostly it's structured data. It has schemas, so it basically forces you to have like some types or something like that. It allows you to have ACID compliant, so it's basically also like version friendly, for example, and it's also separate from storage, separate compute from storage, right? So the pipeline would look something like this. You have some structured data, be it CSVs, JSONs, or XMLs. Those are the structured data. They are basically processed, so somehow extracting the information from them, or transforming them, or pre-processing, or you name it. Then that's placed in the warehouse, and then from the warehouse, reports are generated. And that is how it works, and it is very nice. It does the job. As I said before, it's ISAT compliant, and it's also standardized. So because it is standardized, it's actually very cool, because, well, it could be, because you have schemas now, you kind of know, okay, so this is how the data should look like. So you can tell your customers, oh, this is the output of the data, and it will always be exactly the same. However, it is expensive to implement and maintain, because sometimes the databases fail, sometimes you have to scale them, and that's a, let's say, not an easy process. It's also not good for unstructured data. So unstructured data is, just to remind you, images, videos, audio. You cannot really store that in a table. So, and now we have a lot of such data, so we have to somehow manage that. And it has a very rigid structure, so it's kind of sometimes hard to work with it. This is where lakes came to be. So yeah, Delta Lake. So this is the lake part of it. It can store all kinds of data, so it can be unstructured and structured. And it also allows you to have the schemas, and it allows you to store raw data. First of all, it's future-proof, because there's a wide variety of support. There's a lot of applications and tools that actually handle Delta Lakes. It's very much cheaper, because it has more efficient processes under the hood. And it's also very flexible, so you can handle any type of data, and it will be stored there and processed there. However, yeah, the performance can be lacking, and yeah, the performance. Oh yes, yeah, the performance part is not good, because, well, before you actually put something into the Delta Lake, you have to pre-process the data before you actually put it in there. So that's kind of slow and can be like a bottleneck in your pipeline. Also, the Delta Lake is usually used like a dump for all the data. And yeah, kind of from the name it stems like that. You just dump all of the data in there and just exists somewhere, right? And yeah, it's not really business friendly. So it's kind of hard to, for example, generate reports from that, because you have just a huge amount of data somewhere, and somehow you have to make reports from that. That's kind of hard. Yeah. So this is where the lake houses come in. Lake houses are basically a hybrid approach of the previous ones. So they both, it uses Delta Lakes as under the hood, but also allows you to have, yeah, structured data, unstructured data. It's ACID compliant now. It has schema support and also data governance. So under the hood, it would look like something like this. So you have the unstructured data and structured data coming in. It is stored in the Delta Lake, so it's basically all dumped in there. But then on top of that, you have the metadata that actually tells you, okay, well, this is where the data came from, this is how it's going to be used, and information like that. Also, it now allows you to be more secure, right? Because you can now say in the metadata for whom this data should be accessible to, for whom it should not be accessible to. So it is much more compliant with the government needs, or safety and privacy. And then from that, you can also generate stuff like reports, data science, and machine learning, because you can also state in the metadata where the data is going to be used, right? So when what you want it to be for a report, sure. If you want it to have for machine learning, then you state that somewhere in a tag or something, okay? So this is how lake houses are structured in terms of storing the data. Yeah, it has a bunch of pros, because, well, it's basically a combination of both previous tools, and yeah, it has all the pros of every one of them. It's very future-proof. It reduces redundancy, which is actually a very nice topic because many companies, what they do is they have multiple places where they store their data, and that's why the data is duplicated, and that's, well, quite redundant, right? So you don't really want to do that because you would just pay for all of this data to be stored, but then like it's actually the same thing, so you're basically wasting your money. It's cost effective for similar reasons because it's very fast to process and also stores more efficiently. It supports different workloads, so you can have, for example, parallel machines working on it, but we'll talk about that later. And also supports versioning, so that is the ACID part of it, right? So you can know, oh, if this is corrupt, then you can go back, refix something, and then bring your new data. Yeah, so this is like houses on how they store data. Now processing data, and yeah, again, nice imagery. So we'll talk about Lambda, Xi, and Delta architectures of how to actually process the data. So first of all, batch versus streaming data. So first, batch, what is batch data? It's basically when you have a bunch of data, for example, images of cats and dogs, for example. When you want to do like a machine learning task, you have some images of cats, some images of dogs. You can classify them, you can work with them, and do whatever you want. You can find the mean and everything, right? So this is batch data. You have it accessed at the same time. Streaming data is something different because it is always updating. It's always changing. It's always becoming something novel. So we cannot really tell what is the mean value of the data because it's always updating. So essentially, if you, for example, take the mean of the data, you can only do it for the subset of the whole data. So you can create a mini batch, for example, the first 3 or the last 2, average that, and then that will be your data stream. And the interesting part about this is now, because it's a stream, when you do some process on it, the other thing that you get is also a stream because, well, the process will always be changing. The process will be the same, but the data will be always changing. So you always have the new output stream of real-time data. How do you hold that and how do you manage that? So usually it would be something like you have a data source, it goes through a, let's say, speed layer, which is basically very fastly processing streaming data. And then it has a like real-time serving layer. And then you have a batch layer, which actually processes data in batches, okay? And then, yeah, you have a batch serving layer. And then when you actually, as a user, want to figure out how's your system doing, you make a query to the real-time or the batch one. And that is doing the job, it works, but it also has some pros and cons. It's, yeah, good to balance between speed and reliability, deals with historical data, but it is a coding overhead because you're now making basically 2 branches, which you both have to maintain. You have to both think about them. How are they working? Are you sure if they're working correctly? And just in general, it's very cost inefficient because now you're doing double the work and it's challenging to implement, and yeah, it's redundant. So basically redundant, not cost effective. We have to have something else. This is where the Xi architecture comes into play. So now we just remove the batch layers and we just have a streaming layer and the serving layer for the streaming layer. So basically it is creating a new stream, like I said before. So you take the stream, you batch it into batches, for example, of novel data, you process it, and then you have it as a streaming layer, and you as a user make queries to the serving layer. And that is nice. It's a simple architecture. It's simple to make yourself, like a one system architecture, but it's suboptimal for batch data because, well, now your batches are always updating, they're always changing, so you don't really know, like you don't have a constant information, let's say. How do you join data, right? So if you have like 2 types of data, you have to join them, but it doesn't really work because your data is always changing. How do you deal with out-of-order data? So for example, corrupt data or data that is old that you don't really want to manage. Basically, it poses a lot of questions that are kind of hard to manage yourself. So we need a novel approach. This is where Delta architectures come into play. So it's very similar to the streaming part, right? So it also has streaming in the bronze, silver, and gold layers. However, it's a different way of thinking about it. So in the bronze layer, you have all the raw data, right? So when you collect the data, it can be everything from like all of the sensor measurements, everything. You just dump everything in the bronze layer. In the silver layer, you have some processing done in it. For example, you clean the data, you make it more manageable, you make it more durable for the people, so that the data scientists, for example, can do something on top of that. And then the gold layer is basically the final layer, which could be used for like business goals, right? So if you want to have a report, a data scientist could write like a pipeline from silver to gold, which would process the silver data, which is structured, into the data that is only needed for the business people to take action, right? And so that is what is stored in the gold layer. And then the business people basically make queries to the gold part, but also the fact that everything is stored in the bronze, silver, and gold, you have access to all of the data from before and after processing. And this is very nice because, for example, if someone has forgotten or someone has lost something while processing, you can always go back to the bronze part and redo it. And then you'll always get the new results. It's very, let's say, efficient. So it's best of the both worlds. It allows you to batch data. It allows you to work with streaming data. It's very straightforward and easy to think about. It allows you, the cons, one of them is like you have different versions of the same data that is required. I would put it as a pro and a con, but yeah. And yeah, the con is also, it's not really battle tested because, well, it's quite a novel approach. It's quite novel and it hasn't been tested enough to actually tell if it's good or not. But from the idea itself, it seems very nice. And yeah, I've also personally worked with it. I love it. And I think it's very useful. So yeah, this is Delta Lake. It's a combination of how we thought processing in a medallion structure, so bronze, silver, and gold. And also it's a way of storing data, right? So all of the data is stored in Parquet files. Those are specific to usually how you store it in the cloud. That's how you store the files. It has ACID transactions, so you have versioning. You can always roll back everything. If there's some process that is going on, it is interrupted, and it is interrupted, then nothing on the table actually gets corrupted. It has perks of batch and streaming, and it is compatible with Apache Spark, which basically allows you to have an interface through like Python or SQL and many more applications. Yeah, I thought we could also watch a video on how lake houses work in practice. So I'm gonna turn it on real quick. Other than that, does anyone want to have questions? Because I'm gonna just start the video and we could watch it.
Not so far.
Okay.
Writing out your tables with Spark. The Lakehouse is a simple and open data platform for storing and managing all of your data that supports all of your analytics and AI use cases. Delta Lake provides the open, reliable, performant, and secure foundation for the Lakehouse. It's an open-source data format and transactional data management system based on Parquet that makes your data lake reliable by implementing ACID transactions on top of cloud object storage. Delta Lake tables unify batch and streaming data processing right out of the box. And finally, Delta Lake is designed to be 100% compatible with Apache Spark, so it's easy to convert your existing data pipelines to begin using Delta Lake with minimal changes to your code. To get started with Delta Lake, when writing out your tables with Spark, instead of Parquet, simply say Delta. You can also use SQL to create a Delta Lake table from scratch with the Create Table Using Delta command. Or you can use the Convert to Delta command to convert your existing Parquet files to the Delta Lake format in place. Now that we've converted our data to Delta Lake, let's look at the data in our table. We have 14,705 batch records in this table, and you can see here what the data actually looks like. Next, I'll show you how Delta Lake is able to handle batch and streaming data with ease by setting up 2 streaming writes to our Delta Lake table alongside 2 streaming reads that will happen simultaneously. So as you can see in this chart, the initial 14,705 batch records in our table are still present, but new data is now streaming in from Stream A and Stream B at around 500 records per second each. Each new bar represents a 10-second window, during which both Stream A and Stream B are writing to our table concurrently. Meanwhile, Delta Lake can also serve consistent views of this table to our streaming read queries, which are powering the visualization below. Finally, just for good measure, we can throw in a batch query. So, how is all of this possible? It's possible because of ACID transactions. Delta Lake uses a transaction log that serves as a master record of all changes made to each table. That also determines which files are part of our table at all times. You can view the transaction log at any time by running the describe history command. When we run this command, you see that each write to our table has been recorded atomically as a streaming update. Once a new write is recorded in the transaction log, all of our downstream readers will now include that write transaction in their view of the table immediately. So everyone always agrees on what constitutes a Delta Lake table at all times. They simply refer to the transaction log. This all makes Delta Lake tables really powerful. And at Databricks, we found that many of our customers are able to simplify and streamline their overall data architectures using Delta Lake. By building a simple multi-hop data pipeline with Delta Lake tables, you can reliably transform raw batch and streaming data into high-quality structured data that multiple downstream apps and users can query at once. And what this means from a business ROI perspective is lower cloud computing costs, less complexity to manage, and less time wasted on fixing systems issues like corrupted data. But Delta Lake does a lot more than just use ACID transactions to combine batch and streaming data. It also offers tools like schema enforcement to protect the quality of the data in your data tables. Without schema enforcement, data with mismatching schemas can break your entire data pipeline, causing cascading failures downstream. So, we use schema enforcement to ensure that that doesn't happen. But schema enforcement alone is not enough. In the event that we do want to change our table schema, we also need schema evolution. With Delta Lake, we evolve our schema quickly and easily by simply adding the merge schema option to our Spark write command. And when we run this command, we can see that the write command that previously failed has now occurred successfully. And the new credit score column is now present in our table. Another major feature of Delta Lake is the ability to travel back in time using time travel, also known as data versioning. Because every change to our table is recorded as an atomic transaction in the transaction log, we can use this information to recreate the exact state of our table at any point in time. Time travel helps you avoid making irreversible changes to your tables. It makes your data sets and experiments reproducible and offers a verifiable data lineage for audit and governance purposes. So let's first review the transaction log using the describe history command that we saw earlier. And as you can see, each version of our table is saved by version number and by timestamp. So we can use this information to do things like query historical versions of our table. So let's go ahead and do that. By adding the version as of command to our SQL query, our query runs on the very first version of our dataset, version 0, and returns a count of 14,705, the same number of records that were originally present in our table. Taking time travel one step further, we can roll back our table at any time using the restore command shown here. This is really useful if we decide that we've made a change to our table that we want to completely undo and simply roll back our data to an earlier version. So as you can see, now when we query our table, Those original 14,705 batch records are the only records present in our table. Version 0 has become the current version. The next Delta Lake feature I want to demo for you is full support for transactional DML commands like update, merge, and delete. These are the SQL commands that make manipulating big data tables quick and easy. Before Delta Lake, deleting a user's data from a data lake to comply with a GDPR request was difficult to perform without running the risk of data loss or corruption. But with Delta Lake, we can delete a user's data transactionally in just one line of code. First, let's view the user's data. We'll choose the user with loan ID 4420. And now when we run this delete command, you can see that our user's data is successfully deleted transactionally. The same idea applies with other DML commands like insert, update, and merge. Delta Lake makes these operations really simple to perform with minimal code, all backed by the reliability of ACID transactions. So let's go ahead and use time travel to insert that user's data back into our table. And when we run the command, we see now in fact there is a record in our table with loan ID 4420. Next, let's go ahead and update our user's data with a single command as well. Here, we're going to set the funded amount equal to 22,000 for the same user as before, number 4420. After running the command, we see that the user's funded amount has been updated successfully. Finally,
So yeah, the rest of the demo is going to be about just like modifying the data and then the fact that you're going to come back, isn't it? Using rollback, for example, the ACID transactions. So yeah, I wanted to show actually a live demo on my own, but then yeah, it's all the data we have is NDA protected, so I cannot really show that actually. So yeah, I had to show a video. But basically, to be honest, you don't really work with the data lake on itself, right? So you use usually something where it is combinable with. So something we use in our company is Databricks, and this is actually also something that you can try on your own. Yeah, so basically Databricks, Databricks is a platform that allows you to manage your data, work with data, and to perform similar data analysis. And it has Delta Lake under the hood, so it's already based on that, and it is managed by Microsoft. It's very easy to scale, it's easy to process, and yeah, you can also try Databricks. They have quite a lot of courses on how to start and work with data and how to integrate it into your platform. And the nice thing is about Delta Lake is that it's actually very easy to integrate with almost anything because they support basically the majority types of how you would actually initially store something. Then also migrating your code is very simple, as you've seen in the demo. So you just change some stuff into Delta and it just works like magic. Yeah, so that's it for the demo. Yeah, thank you for watching the presentation, and yeah, if you have any questions left, feel free to ask.
The bronze, silver, and gold.
Yes.
If you have 40 terabytes of petabytes, make you copies, or is it an extraction of a few on the bronze data?
Yeah, let's go through how would the medallion structure work on top of like the Large Hadron Collider. So the initial raw data would be just everything that the Large Hadron Collider produces, right? Maybe some of it will be filtered, but it's basically the raw data that is put in the pipeline. Then in the silver structure, you would have some more process data. So you don't really need to know what was the voltage at this specific sensor, what was this specific sensor doing, what was here happening. You need to know the general picture of it. So for example, of one slice of the Large Hadron Collider, how was it doing? So you actually process that into bite-sizable data and that is stored in the silver part. And then in the gold part, this is something what the final researchers would need. So they would need a general overview of how the whole system is doing, what happened in this space, what happened, where something has happened, for example, where the atoms hit each other. So this is going to be also processed from silver and then put into the gold place. And then, yeah, this is where the people look at it.
Map reduce, is that a solution for this big data, like Hadoop?
Hadoop is integratable with Delta Lakes,
Okay.
and but Hadoop in Delta Lakes, this is a specific place how do you store the data itself. Hadoop is, as far as I remember, it's for actually processing and working with it.
Yes.
Yeah.
And the big data that you mentioned before, how many duplicates are there?
Well, yeah.
And because you said at first that 90% of the data is from the last 2 years.
Yes.
I heard that 2 years ago also. And 2 years before that also.
Yes.
So, and it's actually true. It's exponential growth of data.
Yeah.
But how many of it is actually duplicated?
Well, I cannot really tell how much of it is actually duplicated, but I'm pretty sure it's a lot. But also, it's not only just duplicated, it's reformulated, it's restructured, right? For example, even in our gold, silver, bronze architecture, the raw data is always accessible to anyone, but then it's the silver part, so how do you actually process it, how do you make it into something that is actually bringing value. This also could be like a duplicate, right? Because it's actually the same data, but it has been processed. But still, it's also new data because it's bringing new information to the table, which was not there before. So it's a very complex question, and especially like I don't really know how to even analyze the whole internet of things. Like there's a lot of things that are in there. Yeah, I hope this answers your question.
Meer vragen? Nee?
Right. Yeah, thank you very much. Also, just in case, if you like this talk, we at Researchable host Hot and Spices every first Friday of the month. And fortunately, this Friday is the first Friday of the month that we will be hosting our Hot and Spicy. This is basically a place where we share technologies and very interesting stuff. So this Friday we'll be talking about graph neural networks and how are they applied in real life. This is actually what I'm doing my thesis on right now, but there will be also some other company joining us and talking about that. So you can also join online or join us at the office. And yeah, our office is actually located very close to here, also at the Zernike campus. Yeah, thank you for watching, and I hope you have a great day. Yeah.
Thank you.
Well, thank you, Mansoor, for talking about Delta Lakes, data warehouses, data lakehouses. I remembered it all. Jullie ook allemaal bedankt om hier bij te zijn. Iets korter gastcollege dit keer, maar goed. Ik ben ook wat eerder thuis, dus misschien is het ook helemaal niet verkeerd na zo'n lange lesdag. Tot de volgende keer, volgende week weer een nieuwe module. Top, tot de volgende.
Thank you.